So, hi everybody, and welcome to this talk. I'm sure you're familiar with Schrodinger's cat. The cat is in a box, and it's only when you open it that you know if the cat is alive or if it's dead. So, maybe there are such a thing as Schrodinger's field, a field that can be both mutable and immutable at the same time. And it's only when you look at it that you know if it's immutable or not. So let's join me in this kind of journey in a sneak peek at the StableValues API with the code cry, codes like lazy initialization, but performs as a constant. My name is Permin Bar. Here is my social handle, and I work in the Java core library teams at Oracle. And here we have the agenda. I'm going to reveal right now that I only have 10 slides, so most of this session will be live coding. So I'm going to talk about the motivation for stable values. We're going to describe what is stable values. We're going to do some benchmarks and see how it performs, and talk about the evolution of stable values. How can you create your own stable constructs? A small summary, and then we're going to have a session with questions and answers. Now, before I start, the stable value is just a single class in the API, in the JDK. So it's not a super big thing, but it's a new concept. So what does stable value actually provide? Well, this is kind of an attempt to boil it down to something shorter. It's a deferred shallow immutability. So it's immutable, but it's not immutable directly. You can do it immutable later. And this can give significant performance gain and also give you a better code. It's easier to read, and it's like easier to code. So that sounds like a big promise. So let's see what we are looking at here. So this is my copy of Effective Java, and there you can read item 17, minimize mutability. So we have this tension between mutability and immutability, and I think the stable values can kind of bridge some of the rift here. Now, stable values is described in a JEP that recently was proposed to target to 25. So it's very likely that we'll see a preview of stable values in JDK 25. In fact, I provided a PR for this functionality, and it's in there, so you can go there and comment, or click on the rocket symbol or whatever if you think this is a cool thing. So with that, I'm going to go head over to live code. So hopefully it's here. Yeah, okay. Okay, so let's look at a typical enterprise application. A typical enterprise application consists of a lot of controllers that does things. For example, an order controller. So I'm going to show you what the order controller is here. The order controller, in my simple example, only has a single method, that is submit order. And you submit the order for a certain user, and you have a list of products. Nothing peculiar there at all. But the question is, how do we implement such a controller? I'm not going to worry about the actual business logic here. In the examples here, I'm only going to talk about loggers. So I have a logger here, which is an instance field. Now, I know you think, why didn't that guy make it a static method? But that's not the objective of my presentation. You could do that, but that means that you only have a class kind of field called logger. Maybe you want to have several logger instances. So you have this logger here, and you create it up front. And when you are running submit order, you can use that logger to log messages. Nothing strange there. But the problem is, as soon as you create the order controller, you need to create this logger. And maybe you don't even need it. Maybe the logger is disabled. So why pay the price of creating it up front where you might not even need it? So that is the thing here. And if you look at the typical application, well, here I have 3 controllers, but in a real case, you might have 100 or 200 controllers having different responsibilities. And each of them have their own loggers. So in this case, it's going to be like 6. You have to create the order controller, and that in turn has to create the logger. And the logger in turn might have to create files or directories or connect to a database or whatnot. And that might be really slow. So that's the reason why we have 6 turtles up there. One for the actual controller and one for the corresponding loggers there. So we can try to get around this problem by having a mutable field. This field is just private, and then we add this kind of method that's called getLogger that will check, do we have a logger? Is it null? Well, it was null. Okay, then I must go ahead and create it, and then I just return it. And while this looks good on the surface, maybe you see the problem here, but it's not so good because now the VM is not able to trust this field, the logger field, because it can change. So it cannot constant fold the field. And what is worse is that if you are now deploying this in a multi-threaded environment, you expose yourself to a huge array of problems. Not only can you create several loggers because there might be races between the threads, but you also can see data that is not really correct. So how can we solve that? Well, a very simple solution is to serialize access to the logger. You can synchronize this method, and of course this will be detrimental to performance because now suddenly only one thread can get the logger at the same time. So this will create kind of a bottleneck, which is not good. And still, you can't constant fold the field because it can change. The VM is not able to see through this code and see that, wow, this value can only actually be updated once. So we can improve it further by using something called, something called the double-checked locking idiom. So that relies on first checking the value, and if it's set, well, then we're good to go. Then we just return that value. But if it's not set, then we need to synchronize because another thread might be in the process of creating this or has already created it, but I'm not seeing it yet. So therefore, we need to check again and read the field, hence the name double-checked. And then if it's truly null, now we are alone. So then we create it, and then we return it. And this works, but it's very brittle. So for example, if you forget to declare the logger as volatile, you expose yourself to problems. You can see objects that is not fully initialized or partially initialized, which is very difficult to understand if you're not fully understands the Java memory model, which very few people do. Okay, and we still have a problem that you can't constant fold this. And I think you can imagine that this is just a scalar value, a single value, but if you want to hold an array of stuff, for the sake of reasoning, I have here an array of loggers. Maybe that's not the most straightforward example that you need in daily life, but it still shows the problem that if you have an array, you can't declare the array as volatile because that only declares that the reference to the array is volatile, not the elements themselves. So then you have to fiddle around with, for example, a var handle here and do explicit volatile access by yourself. And here, because you're in the lock, you don't need volatile, but then again, when you set it, you have to use volatile access. So that is very error-prone and not something you want to do. Of course, if you want to use a static field, if you only have one instance, then it's okay to have static, and then you can leverage the class loading, class holding idiom like this. So you have a holder class, and it's only when you instantiate that class that the logger will be loaded. So this is actually lazy loading the logger here, but it's not an instance field. And this is not really scalable because if you have, suppose you have hundreds of these, then you must have hundreds of internal classes. And maybe they are connected to each other and creating this dependency tree, and everything goes down the drain very quickly. Another thing you can do, let's go back here. So this works, but it's kind of an elephant instead of a turtle because this mandates to create a new class, and that is allocating a lot of static resources. Another way you can do is that you can use a concurrent hash map. So I can say that I have a private final hash map here, and if it's absent, I invoke this lambda or method reference here, and that actually looks pretty good. I mean, from a readability perspective, I don't have any objections. But it's like slow, and it's a lot of overhead because a concurrent hash map contains a lot of things you really don't need, like entries or keys or things like that. So I hope with that you understand the motivation for stable values. There is actually no construct today that fits the requirement that we should be set a thing only once and then use the full kind of capability that the VM offers us. So enter stable value. So here we have a stable value. And when we create it from the beginning, it doesn't have any content. It's empty. So the stable value is empty, but it eventually will contain something of type logger. And then our getLogger method will look like this. It will return what's in the stable value, or else, if it's not set, it will invoke this lambda here. And this is kind of the recipe. How do I create the thing I have in my stable value? And the StableValue API guarantees that this lambda is only ever invoked once. So that's a guarantee that's placed there. So that's good. So this is better. And the VM is able to, because it knows what a stable value is, it knows that if it's set to a value, that value can never, ever change. And so it's able to constant fold that value and optimize our code once the JIT compiler kicks in. That's important. And actually, you can do the same with all the controllers. So you can say that my orders here is also a stable value, but it's not set yet. And then you can have access to orders. You return the orders, and here's the recipe, unless you have it. Same goes for product repository, and so on. So this is quite nice, but we can do better. Okay. So here's what you can do. So there is not only a stable value, but there are stable functions and stable collections. And one of the functions that we provide out of the box is a stable supplier. Now the stable supplier factory takes another supplier. So this is all about caching. So you say that here's the supplier, but I will only invoke that at most once. And once it invokes, I will memorize that value, and then kind of from the outer supplier, I will just return that value and never invoke this kind of backing supplier that's there. So it's kind of caching, you can say. But it's made in such a way that it's guaranteed that this value is only updated once, and hence the VM can trust the constant value and is able to constant fold it. So eventually, when your code goes hot, it will just be a constant, even though you might have updated it much later than when you created the actual supplier. So we can do the same thing here for orders, products, and users. And if we look at our specific order controller, it now looks like this. And I think this is much more nicer, because now we declare the stable value and the logic in the same place in the code, and we can get rid of the invariant that we have to use this get method. And instead, we can use the supplier directly, because now the supplier only have one method, of course, because it's a functional interface. It only has a get function. So I think this is, now it's getting better. Okay. So what do we have here? So maybe, as I mentioned, maybe we want to have several order controllers, and maybe we want to share them across threads. Maybe an order controller can block, so we want to have several order controllers. And there is something called a stable list. As I mentioned, there's a stable supplier, but there are also stable collection, and one of the collections we provide is a stable list. And as you can imagine, a stable list has a certain size, and it has elements, but the elements are not produced yet. We only have a recipe of how to produce the elements once they are needed. And in the same fashion, once they are created, the VM is able to trust that that element will never ever change, and so it can constant fold it the same way as with the supplier or the stable value itself. So here I said that I have an order pool with a pool size, which is 16 here. And when I go in and have this order here, I look at my thread ID, and then I just divide them with a mod operation and pick one of the implementations of the order. And so this will constant fold as well, because order pool.get for a fixed index will always get the same order controller. Okay, that's the basics. So now let's go and see what we can do with stable values in our everyday life. So one of the things we sometimes come across is how to make a singleton. And I know I can make a singleton using the class loading idiom, but here I'm showing another way of doing it using stable values. So I have my singleton here. It doesn't matter what it does, but I want to make sure that only ever is one my singleton created. So I can use stable values for that and say that here's my singleton supplier, and here's the recipe for that. I have a stable value supplier, and this is kind of the inner supplier that's only invoked once, and then I just delegate to that with my getInstance method. So singleton supplier.get the first time will invoke this lambda up here that will create my singleton and then return that value. But the next time I invoke get, I know the supplier that is returned here already knows that there is a value, so I can just ship that value instead of invoking the lambda that's supplied up here. And of course, I can create much more complicated constructs like this. I made this kind of joke to call it a tringleton that only has 3 instances. So I can say that I have a stable value int function, which corresponds to a list. And the int function takes an int and then returns something. And it has 3 allowable inputs, 0, 1, and 2. And for that, they return something that's created with this lambda here. And I don't care about the index when I create them, I just create a new singleton. So therefore, eventually, I will have 3 singletons, but they can be constant folded, the lookup of them. So if I have like getInstance 2 will be constant folded to actually that value of my singleton, and the VM will run much faster. Okay, let's look at another more general case. I think it's very common that we are using non-evictable caches. So for example, we have a bunch of keys, and then we want to associate some value, but we don't want to calculate that value up front because it might be expensive. I have a very simple case up here when I'm using square root, which is actually quite fast, but this is just for illustration. So I said that I have a stable function, which is the most general function we provide out of the box for stable values. And the stable function should have these kind of allowed inputs, 1, 2, 4, 8, and 16. And when I want to calculate the actual cached value, here is the lambda for that. And of course, I just invoke strict math square root for that. And you can see here that the similarity between a stable function and a stable map, they are basically the same thing, even though a map contains all the bells and whistles that you need in order to implement the map interface. But fundamentally, they rely on the same solution. So the reason we provide stable collections is that there are some APIs that takes a map or takes a list. And then you can very easily say, well, here is a list, but it's not populated yet, but I can just ship it. And maybe the method you are calling only uses the first and second element, and I don't have to compute all the other 100 elements that I don't use. And if we go down here, if I kind of invoke this square root cache, apply for 16, once the JIT kicks in, the JIT will see that the stable value is trusted, so it can constant fold 16 to 4. And this will equate the performance like I have written the literal 4 here. And that is very good indeed for performance reasons. Okay, so let's look at more kind of convoluted examples. I think you are familiar with the Fibonacci series from computer science school, or maybe you have read about it on the internet. The Fibonacci series is the sum of the 2 preceding elements. So for example, 5 is the sum of 2 and 3, and 8 is the sum of 3 and 5, and so on. And it's very easy to devise the logic for this using recursion. So if the value is less than 2, it's the I value. Otherwise, we invoke recursively this method here. And the price for being simple is that it has a very high complexity. It can be shown that this has an exponential complexity. So as I grows, the complexity grows a lot. And I can fix that with stable values. So here I say that I have a list of up to 46 elements. It turns out that the magnitude of Fibonacci series grows very quickly in the end. So it turns out, when you look at it more carefully, that 46 is the highest value you can input in order to represent that as an int. If I would have chosen a long, I can have a much bigger number here, but 46 is the number. So I say that I have a stable list that is 46 elements, and here's how to compute them. I just invoke my fib method here. And in the fib method, well, if it's less than 2, it's the same as before. I return the value I have. Otherwise, I recursively go back into the list I have and say that I want the element -1 plus the element -2. And StableValue is actually able to figure out this dependency tree and still be able to constant fold values using solution like this. So this will turn the exponential function into, the first time I call it, it's order n, and then from that it's just an order 1 operation. And of course, this is not unique to StableValue. You can do this with a normal list, or you can do this with a concurrent hash map, for example. But the performance will be very different, as I will show very shortly in the benchmark. So let's head over to the benchmark. So I'm going to start it now because it takes some time, and then I'm going to open it and show how it looks like. So I've started the benchmark in the background. It's running, and here you recognize the example I had 46 elements. I invoked the stable fib, and the stable fib looks into the list. And here's my benchmark. I just returned the value for fib 10. And here I have a similar solution for a concurrent hash map, which has computes the value here for 10. And then when I run it, you can see here that the performance of the map was like 6 nanoseconds per operation, but for stable it was 0.7. So the stable solution is about 10 times faster than using a concurrent map. And I think that is a very good thing. Actually, 0.7 nanoseconds is just a few clock cycles. So I don't think we can hope for any major improvement over that. Okay. So one of the questions I get all the time when I speak about what StableValue is, why didn't you call it lazy? That's the first question I almost always get. And the answer is, we did call it lazy. We also called it computer constants. We called it a lot of other names. But eventually, we didn't think that lazy described actually all the properties of stable values, because lazy, yes, it's lazy, but it's also a guarantee that we only compute it once, and that's not really packed into the concept of laziness. But the good news is that if you want to call it lazy, then here is the recipe. You can do that. It's pretty much a one-liner. So if you want to call it lazy, you can construct your own lazy, and this is just one example of how you can use the building blocks of stable values to create your own stable constructs. And as you can see here, you have a lazy which implements supplier. So lazy has just a get method. And I have a static factory up here that is creating a stable supplier of the original supplier. And then when I invoke get, I just delegate to the get method of the stable supplier here. So basically, this is just changing the names of the class. And this will perform equally well in terms of constant folding as StableValue will. As I will show in a benchmark, which I will start right now because it will take even longer time, and then we can have a look at that. So let's see, micro lazy bench. So it's running now in the background. I'm going to open that, and now it's going to be a little bit more complicated, I'm afraid, because I'm testing a lot of things here. But first up is the definition of lazy, which is exactly the same as I have shown before. Then I have my original supplier, which I made purposely slow by invoking this park method here. So this will make the invocation of the supplier super slow. And that's my intention, of course, because I want it to be obvious whether or not this method is called. Then I have some static field. I have a stable, which is a stable supplier, and I have our makeshift lazy of integer, which should be the same. I promised that, so let's see if my promise is correct. And then I have not static fields, but instance fields of a stable supplier and a stable lazy. So there's a difference here. You know that this is static fields, and these are not static fields. And we are going to see a difference in that. Then I have two holders. I have a holder in the form of a record that holds a supplier, and I have something that is very similar. I have a class holder, which is a normal class, which holds a supplier, and the constructor sets that value. So it's very similar to the record holder, and we're going to see how the difference performance, and that's going to reveal quite of, I would say, an unfortunate property of stable values, which I will explain more in detail later on. And so we have a record holder of the stable supplier, and we have a class holder of that. And then are the benchmarks. So when I run them, you will see the result here. Let's make it bigger. So first of all, we can see that if we have a holder class, can you see this? Yeah, okay. So the holder class is slow, whereas the record class is fast. And why is that? Well, that comes down to trustability, because if you look here in the normal class, it declares a field, and you can change this field. Even though it's final, you can use reflection and use this set accessible to true, and then you can change this value. And therefore, the VM cannot trust that this value will not change. And that's unfortunate, but that's the case. Whereas a component in a record cannot be changed by set accessible, and therefore the VM can trust it. It's even better than that, because you can't even discover the offset for a field in a record using unsafe, but you can do that with a normal class. So that is the reason why the VM does not trust instance variables in normal classes. So I will talk a little bit more about how we can circumvent that kind of restriction. But for now, it suffices to say that if you can use a record, that's good enough. And we can see that instances are not constant folded because they are instance variables. They're not really trusted. But we have about the same performance for lazy and stable here. And if we look at the static variant, we see that lazy and stable are about the same. This is within the error of margin. I purposely didn't run this benchmark for a long time, because then you guys have to wait. So therefore, I promise you that if you run it for a longer time, it will show about the same value. And of course, the original was super slow, as expected. Okay, so that's that. So let's look at trust. I know that trust is hard to find these days, even for the VM. But in order to constant fold, it needs to start with something called a constant. And a constant is a static field. So it needs to start with the static final field. And I name, for example, this A here. And then there must be a chain of trustability in such a way that an instance field must be final, and it must reside in a record or a hidden class, or a class that internally has a field that's marked with stable, and that's only possible within the JDK itself. But the good news is that you don't have to remember these rules. There are some rule of thumb under here. So, for example, a method reference is implemented using a hidden class. And if you remember lazy class, for example, that uses a method reference. You have this colon, colon, and something, and that results in a hidden class, and therefore that works. Immutable collections like set-off, map-off, collectors to a modifiable are backed with stable fields. So if you use them, you automatically get trustability. And hopefully, we had Ron Pressler had a presentation of integrity by default. And when we get that, we will also trust instance field. So final actually means final. And there, this restriction is going to be lifted. And hopefully that is going to be made before the stable value goes like a final feature. So in this example, we have, this is a constant anchor. We have A, B, C, D, E, F, which are all trusted, might reside in a record or a hidden class. Or we have A, B, big C, D, E, F, where C is a private final field or a final field, static field. That's trusted, but as soon as we have something that is not trusted, the trust goes away, and it can't be constant folded. So let's look at some examples now that we're armed with this knowledge. So how do we, for example, produce a stable predicate? Now, a predicate is something that takes something of type T and then applies a test to it, and then it returns true or false. And you can do that by just delegating to a function, because this function here goes from T to Boolean with the big B. And then you can just say that I want to apply that method, and that's my predicate. And as you can tell, these all rely on method references, and so we will have a hidden class here, and that will mean that performance will be retained when we're trying to constant fold this value. So here I have created a custom stable predicate. That was relatively easy. It's getting a little bit more tricky when we have more than one arity functions. So suppose I want to create a stable by function that I want to be constant foldable. Here I made a small trick. I've introduced a record that has a left and a right pair. I could instead use the map entry, for example, but I didn't. But the trick here is to use a record. So what I will provide at construction with my record is that I want to have a map with T and a secondary level map with U. And then I'm going to have a stable value there. And I also have my original by function, which I want to make stable, so to speak. And once I have that delegate here, the only thing I need to know is to get for the T, get for the Y, U, and then I have a stable value, and then I take that stable value, but if it's not set, I invoke my original function here, my original by function. So it's pretty easy, and this, try and catch stuff is just if this is null, or if this is null, I will get the null pointer exception, and then I know that my T and U wasn't really there from the beginning, because I need to specify up front which kind of allowable inputs do I have. And so when I have this one, I only have to construct this kind of mappy map. And I can do that by streaming over all the inputs, extracting the left hand for the first level, extracting the right hand on the next level, and then I just create a bunch of empty stable values into that secondary level map. And then it's very important to use map copy off, because all of these collections needs to be immutable in order to be trusted. That's what I talked about before. They must use the internal stable value notation. And this will have the same properties as a normal stable function. It's possible to constant fold this. And in fact, you can have, in this trust utility, you can create this kind of method that takes a type that you have constructed, and if it's shallowly trusted, you can see, is it a record or is it hidden? And it's a very easy way to check whether or not your new stable construct meets at least the first and requirement to be able to constant fold. Okay, so now I can create this kind of a heterogeneous container with all my components that is stable. So maybe I want to provide a list of all the components I'm using. I'm using an order controller, product reporter, product repository, and user service, and then provide a corresponding recipe to create them lazily. And then I have this stable container here, which is using the same trick as before, using record. And it's just a map from the interface and to a supplier that can supply that implementation. And then I have a factory that is streaming over the providers, creates an unmodified map with the provider type, and then I create just this stable supplier that I'm supposed to invoke every time I kind of try to scoop up that value. And this will give me lazy creation of all the controllers. And I will still be able to get maximum performance because this stable container is trusted. So when the JIT kicks in, and I have a code like this, components get order controller.class, that's a class literal, it knows that the backing map or container is trusted, so it will always get the same value back on every occasion, so it can constant fold that call. And it knows it will get back an order controller imp, and it knows exactly how that order controller imp looks like. So maybe it's even possible for the JIT to devirtualize the call to submit order here. And maybe if I have a logger that has some field saying that it's enabled or disabled, and that field is stable, it's able to even eliminate all the code for logging if logging is not enabled. So there is this transitive, nice property of stable values. Okay, so armed with this knowledge, I come to my last class. And this is how you can actually implement this order controller with trust. So now I've converted it to a record, and where I provide a supplier for my logger, which is only going to be invoked once. So this is the logger, and the logger get, and here's the factory. So the factory has a lambda, a stable value supplier, and here's the recipe for that. And this will give you an instance variable that is trusted, and it will lazily create the logger, and you will get maximum performance once the JIT kicks in. So that was the live coding session, and we have 8 minutes left, so I think we are good on time. So we call this toward deferred immutability. And here we have the Schrödinger's field. So up into the top, we have mutable fields. A mutable field you can update any number of times, from 0 to infinity. And you can update it from any location in your code. And you can not benefit from constant folding because this field can change at any time. And you can have concurrent updates, but you have to be careful, of course. Looking at the bottom, we have immutable fields, which is always updated exactly once. It has to be updated in the constructor or the class initializer. But it does provide constant folding. But you cannot do it concurrently because the thread that creates or initializes the class is the thread that's eventually going to set this value. That's inevitable. And stable value ends up somewhere in between. So we have a stable value can be updated at 0 or 1 time. And it can be updated from any location, can be updated by any thread. The thread that wins will update it. And it can be constant folded once it's been updated. So if it's not updated, the JIT will defer constant folding. And once it's updated, it will, hopefully do constant folding. Of course, you can never promise that anything is ever constant folded, but it's eligible for constant folding. And so we get the best of 2 worlds. We get the update anywhere property from mutable field. We get the constant folding from the immutability field. And we get the concurrent update from the mutable field. And here is a benchmark for a manual double-check locking and a stable supplier. And as you can tell, it's about a factor 2 or even more. And now you might argue that, well, this is just a few cycles. Why did you work with this for a year or 2? And the reason is, of course, this transitive story that, okay, if you just have one value, well, fair enough. Wasn't that big of a difference. But if you have a component that has a logger, that has a field, and so on, there will be a tremendous difference in performance. So what's the secret sauce? How is this even possible to do? Well, StableValue wraps an internal annotation that I spoke about before called stable. And this promise to the VM, that's an assertion that this field will only be updated at most once. But it's not safe to expose this. So you can tell you can say that stable value is a wrapper around stable values. And it has synchronization that upholds the set invoke as once invariant. And all the stable functions and stable collections I showed carefully observe this transitive trustability chain. And when final instance actually becomes final in a few JDKs, hopefully everything will be much easier to use stable value, because then you can just use them as any instance field. So, to sum things up, codes like lazy initialization performs like a constant. We have this nice transitive property, order controller logger enable folds, and it's probably even possible to fold code that is a result of a check of that condition. We provide stable values, stable function, and collections. And you can create your own stable constructs using the one we provide out of the box that I have shown here. Even though it's not trivial at the moment, it will be easy. And this will likely come to a JDK near to you soon. So with that, I will accept your hand applause. Thank you. I was just joking. And if you have any questions, please go to the mic and ask. Yes?
As an instance field, it still seems to be very expensive, right? It gives you a little benefit. Like, it's a separate object. It's not a value type, at least not yet. And you lose some of the constant folding. Like, basically, if I'm trying to simulate a lazy vol, right, then it's still not really usable for that.
So I guess the question is, if you're using an instance field and you want to compute a lazy value, is it useful?
Yeah.
Yeah, if you use a record, it's useful. If you have an ability to anchor on some static field upwards. But it's like you will still benefit from it, because even though we thought a lot about constant folding, they are also performant. So if you compare, for example, with the double check locking idiom here, the one that we provide as a stable supplier is more efficient than that, because it's using special memory semantics that is faster than volatile, for example. So it will be a little bit faster than, so it will give a little benefit, even though it's just an instance field, or if you're using it just like a normal field.
Thank you.
Yeah.
Hi.
Hey.
The example with the record for the controller, it's a bit counterintuitive, because records are not supposed to do that. Are we broadening their usage? For me, there are data containers, so
Yeah.
Now you add a lot of intelligence in it.
Yes, so I'll buy that argument, and it's not ideal. So I would see this as a temporary solution, and I think stable value is just a preview right now. So I really hope for this final means final is going to be actually finalized before we finalize stable value.
If it's a final class, it doesn't work?
No, final class doesn't work. So it's a bit of unfortunate, but one alternative will be to not release stable values to preview and wait for that. But we didn't want to do that. We want to get your guys' input. So please try it out and tell me what you think. And I agree that you shouldn't use record like this in normal cases. Yes?
I was wondering whether you could comment on why there are multiple ways of creating stable values. I would have thought the or else set would be the less preferred way of doing it. The stable suppliers seem nicer.
Yes. So we had this discussion whether or not stable, because stable value as such has this kind of imperative function. You can call isSet, or you can call trySet. And these functions are useful in some rare cases. For example, in some JDK internal cases, we need them, or in the compiler itself, we need them. But there's always been the discussion whether or not stable values should only have a lambda and not have this kind of imperative function. Maybe that belongs to something else that is more fundamental. So that is something we have discussed, and in this first preview, we went for this solution, but it might be the case that you're bringing up here that it might not belong here, it might be something else. So that is something we are aware of.
I'd be curious to learn about those use cases, but yeah.
Yeah.
Thanks.
Okay.
Another one, maybe. I was wondering, could we imagine a world where I would just annotate and it will syntaxic sugar it, or I have like the keywords table that would actually do this table instead of all this coding?
So we have that we have that ability internally in the JDK, but you have to be very careful. What happens, for example, if you have a value that's stable and that's getting constant fully, but then you update it? That's a very unfortunate situation. So therefore, we didn't want to expose that. But we did, there is another JEP that's been around for quite some time that suggests to add a lazy keyword in Java. So you can set lazy and have this field, and here's how to compute it. So that might appear in some distant future.
Cool.
And I think we ran out of time. So thanks again for your patience. Thank you.